بسم الله الرحمن الرحيم. الحمد لله رب العالمين والصلاة والسلام على أشرف المرسلين السيدات والسادة الأساتذة، السيدات والسادة المحاضرين، السيدات والسادة المدعوين، الحضور الكريم، السلام عليكم ورحمة الله تعالى وبركاته. يسعدني ويشرفني أن أستقبلكم ولو عبر الآثير وأن أعلن عن افتتاح أشغال هذه الدورة على بركة الله. Honorables orateurs, invités de marque et participants, mesdames et messieurs, bonjour. Je suis ravi de vous accueillir au nom du comité de pilotage et du comité d'organisation de GOL20, en ma qualité de membre de ces deux comités et de président de cette édition. La conférence GOL a été initialement planifiée par un comité de pilotage formé du professeur Ahmed El-Hilali de l'Université Sidi Mohamed Ben Abdallah de Fès, du professeur Jawad Bokhachor de l'Université du Havre et moi-même. J'aimerais rappeler que GOL, la conférence internationale I3E Gestion opérationnelle de la logistique, a été lancée il y a 8 ans à l'Université du Havre et se tient toutes les deux années dans l'une des 3 universités partenaires. Malgré les conditions pandémiques très difficiles qui caractérisent cette édition, nous avons reçu des soumissions de 74 articles de 13 pays différents, dont 62 ont été acceptés pour un taux d'acceptation de 84%. Par la suite, il y a eu 3 désistements. Comme vous le savez, il s'agit d'un événement de 3 jours. Si vous jetez un coup d'œil sur le programme de la conférence, vous conviendrez que cette édition sera chargée et productive. Il y a beaucoup à offrir pour un événement de 3 jours. Je laisserai par la suite au professeur Bokhachor le soin de donner plus de détails sur le sujet. Comme vous le savez, les actes des 3 précédentes éditions de GOL ont tous été publiés dans I3E Explore et indexés par Scopius. Et ça sera aussi le cas cette année. Principalement, le succès de cette conférence est dû au travail d'équipe et à l'aide de nombreux amis et collègues qui ont travaillé très dur pour bien préparer cet événement. Je leur en suis sincèrement reconnaissant. Je tiens à remercier les comités de pilotage, d'organisation, les partenaires et bien sûr les sponsors. Mes remerciements vont particulièrement aux professeur El-Hilali et professeur Bokhachor pour leur rôle pionnier dans l'enrichissement du programme de cette édition, professeur Mhada et professeur Ouzey pour leur travail assidu sur diverses tâches d'organisation, Dr Lamrani pour son aide précieuse afin d'assurer le bon déroulement de la conférence virtuelle en utilisant Zoom, de Madame la directrice Lencias pour son soutien et son parrainage permanent, et tous les conférenciers invités ainsi que tous les participants qui nous ont rejoints pour partager leur précieuse expérience. En terminant, j'espère que vous allez tous passer et apprécier cette conférence. Hello everyone, honorable speakers, distinguished guests and participants, ladies and gentlemen. I am delighted to welcome you on behalf of the steering and organizing committees to the 5th edition of GOL. In my capacity as a member of these committees and the chair of this edition. GOL, the International Conference on Logistic Operation Management, was initially planned by a steering committee formed by Professor Hilali from the Sidi Mohamed Ben Abdallah University in Fès, Professor Bokhachor from Le Havre University in France, and myself. It has been started 8 years ago in Le Havre University and is held every 2 years in one of the 3 partners universities. Despite the very specific pandemic conditions that characterize this edition, we received submission of 74 articles from 13 countries, 62 of which were accepted for an acceptance rate of 84%. This is 3 days event. If you take a look at the conference program, You will agree that this edition is going to be busy and productive. There is a lot of work. There is a lot of work for the 3 days event. I will leave Professor Bokashok to give you further details in this regard. Mainly, the success of this conference is due to the teamwork and the help of many hardworking friends, and I am sincerely grateful to them. I would like to thank the team and organizing committees, the partners and sponsors. My thanks go particularly to Professor Hilali and Professor Bukashok for their pioneer role in enriching the program of this edition, Professor Mhadda, Professor Uzaid, and Dr. Al-Amrani for their diligent work on various organizing tasks, the Dean of NCNIAS for her support and permanent sponsoring, and all distinguished and invited speakers, and all the participants for joining us and sharing their various experience. In closing, I hope that all of you will enjoy this conference. Mesdames et messieurs, je vous remercie pour votre attention. Je vais donner la parole au professeur Karim Baina, directeur adjoint à l'ENSIAS, qui représente Madame la directrice, pour donner un petit mot de bienvenue aux participants. Monsieur Baina, est-ce que vous êtes en ligne?
Oui, je suis en ligne. Est-ce que vous m'entendez?
Oui, on vous entend, monsieur.
Excellent.
Moment de connexion. On est en train de se connecter avec monsieur Baina.
Bonjour, chers collègues.
Bonjour.
C'est sûr qu'on aura de temps à autre ce genre de petits problèmes techniques de connexion qu'on va essayer de surmonter rapidement.
Bonjour.
Bonjour. Nous nous entendons très bien. Monsieur Youssef, vous entendez ou pas?
Monsieur Baina?
Je suis là. Est-ce que vous m'entendez?
OK. Allez-y, monsieur Baina, allez-y.
Très bien. Merci, monsieur le président, professeur Youssef Ben Adada. Dear colleagues, dear PhD students, dear students, ladies and gentlemen, I am Karim Baina, Vice Director of Research, Innovation and Partnership at NCIAS. On behalf of the Director of NCIAS, Professor Ilham Barada, I am very pleased to welcome all participants of Logistics Operations Management Goal 2020 at NCIAS. We are honored to organize this 5th edition of the Goal 2020 Logistics Operations Management Conference by NCIAS. This 5th edition is organized by NCIAS for the second time after the 2014 edition. We salute the great challenges taken up by the steering and organization committees of Goal 2020, whom we thank, and at their head, Professor Youssef Ben Adada, to do everything remotely and to be part of the digitalization strategy of the new development model of NCIAS 4.0 school. We thank our partner, Le Havre University, whom we thank in the person of Professor Jawad Bouchakour. We thank all conference sponsors and partners for their support of the conference. We especially thank the Centre National de Recherche Scientifique et Technique for its support to the Goal 2020 conference. In our NCIAS 4.0 development strategy, we place an important part in bringing together the two academic and industrial spheres, actors of technology push and need pull innovation, in order to carry out joint research and innovation projects and contribute together to the continuous alignment of our training offer, initial and continuing, with the real needs of our country in engineers specializing in various emerging technological fields, so that this Grande École Nationale d'Ingénieurs becomes the hub of excellence and the regional innovation in training and research in the digital sector at the service of society and meeting the real needs of the national economy. We highlight that Moroccan Office of Industrial and Commercial Property, OMPIC, and in his report of October 2020, has placed Mohammed V University in Rabat at the top of the ranking of Moroccan universities and research organizations in terms of granted patents. Aligned leader with the University Research and Innovation Strategy, ENSIAS plans to improve its 30 patents portfolio, its number of PhD thesis defense, 120 since 2014, and its indexed publication with high impact factor and high H index. In this current context of the COVID pandemic, crises are often source of creativity and innovation, and at times industrial renewal, and safety and sustainability are the critical business drivers for the research and the development in academia and industry. During the early stages of the pandemic, the B2B logistics market was impacted and supply chains were seriously disrupted since new regulation were continuously introduced. Diversification and relocation of supply chains to countries closer to home as alternative to some very impacted countries was the key. However, B2C market has exploded as people in lockdown turned to the internet to make their purchases. Not only did volumes grow, the profile of goods being shipped changes, with more consumers ordering even the largest purchases online. Nowadays, there are many pressures now on companies to find creative ways to improve delivery density and cost efficiency. Agile and innovative logistics leader will emerge as they will be able to quick experiment, evaluate, implement, monitor, and optimize processes and resources and employ new technologies to mitigate and meet the changing market conditions. 3 strategic transformation projects to which supply chain professionals can bring their expertise: the digital revolution, social and environmental responsibility, and e-commerce. In the area of digital transformation, supply chain managers can act as a catalyst to extent that they have skills in information systems, artificial intelligence, big data, and Factory 4.0. Regarding the integration of sustainable development in the economic model of the organizations, the supply chain manager can make a contribution to the building with its indicator, measurements, solutions, tools, etc., its methodologies, and its knowledge of stakeholders from the supplier to the delivery person via the warehouses. In the same direction, innovation to improve logistics agility and optimizing operations may be produced by research on data-driven connected logistics-based research, analyzing collected data from operational and planning interoperable systems, from sensors in warehouses, on pallets in transits, and from telematics in trucks and on ships to enable real-time end-to-end digital location tracking of orders, automatic tracking and alerts, route optimization, enhanced navigational abilities, and optimizing routes using data and artificial intelligence-driven system. Those artificial intelligence-driven systems need to be prediction models need to be adapted, since COVID has created a new dynamic for sales forecasting stock optimization, and product recommending system. Also, new technological logistics based on research, based on blockchain, robotics, contactless delivery, early spotting and segregating risks. All of this will lever technological integration. The conference program goal 2020 is very rich. It varies from hospital and pharmaceutical logistics, uncertainty models, machine learning, automotive industry, general pickup and delivery problem, production and inventory management, meta-heuristic, etc. Since economic industrial model for global supply chain and distribution, we would like to wish you a pleasant conference and a lot of thinking, results, and collaboration. Thank you.
Thank you. Right.
Now I'd like to introduce Professor Boukhachor to give further detail on the conference program. Maintenant, je donne la parole au professeur Boukhachor pour donner un peu plus de détails sur le programme de la conférence. Monsieur Boukhachor, s'il vous plaît.
Thank you. Welcome to this fifth Goal 20 edition. We have received 74 papers from many countries: Algeria, Canada, France, Germany, Morocco, Oman, Pakistan, Romania, Russia, Rwanda, Tunisia, and United Arab Emirates. 59 will be presented in 14 sessions. We also have 4 plenary sessions. So I thank my colleague in CIAS and how to take steps to have confidence. Thank you. I'll let my colleague Hilali to introduce the first plenary session.
Thank you, Professeur Boukhachor. Bismillah ar-Rahman ar-Rahim. Vous m'entendez, Monsieur Ben Adada? Vous m'entendez?
Merci, c'est Hilali. Merci, c'est Boukhachor. Monsieur Hilali.
Professeur Boukhachor. Bismillah ar-Rahman ar-Rahim. Bismillah ar-Rahman ar-Rahim. والصلاة والسلام على نبي الكريم. Ok. J'ai la main.
Allez-y.
Oui. Bon. In the beginning, I welcome all for you in your country, Morocco, especially in Rabat city, even if is from a distance. Our speaker today is Professor Ammar Oulamara. Mr. Ammar Oulamara is a professor in Lorraine University. He is an author of 30 articles. He is an author of a great number of books chapters. His main research focus are very diverse, but his central themes and topics are combinatoire optimization, operational research, approximation and complexity, exact and heuristic methods, meta-heuristic. His application field are transport and mobility, scheduling problem, production system and logistic chain, vehicle routing problem, smart grid and the electric vehicle ecosystem. Ammar Oulamara has supervised 10 PhD. He has participated in 17 research projects between coordinator, promoter, and member. Today, the conference given by Professor Amara is entitled Ecosystem of Electric Vehicle from Smart Grid to Logistic. Thank you, Professor, to accept our invitation in Goal 20 conference. You can ask in French or in English. And thank you, Professor. You can begin if you want.
Good morning. First of all, I would like to thank the organizer of the conference for this invitation. The subject of this talk is on challenging problem in the electric vehicle ecosystem. The outline of this talk is as follows. I start with the introduction to electric vehicle ecosystem. Then we focus on three kinds of problem. The first problem is on smart grid, vehicle to grid, and smart charging. The second is problem on location of charging infrastructure. And the third problem is on itinerary and routing of electric vehicle. Then we finish with a conclusion. In the recent year, we talk a lot about the electric vehicle, but we should know that this technology is not new. It has existed since the invention of the car, but with the development of new and more efficient lithium-ion battery technology, electric vehicle has been reintroduced in the market. The electric vehicle is composed of a battery for energy storage and with a capacity between 22 kilowatt until 85 kilowatt, an electric motor and a power control system. The electric vehicle has also some benefits like no emission of carbon, energy recovery during the deceleration, and also low maintenance cost. However, some limitations that prevent its deployment. This limitation are driving range that is between 150 kilometers until 250. It takes time for recharging the vehicle, in which it takes at least 20 minutes until 8 hours, and the insufficient recharging infrastructure and purchase cost. To charge the electric vehicle, there are three modes. The first mode is the simple one, also called mode 1 or slow charging, and the vehicle can be charged between 6 and 8 hours. The other modes are mode 2 and mode 3 or semi-fast charging and fast charging. In the semi-fast charging, vehicle can be charged between 1 hour and 4 hours. And for the fast charging, vehicle can be charged in 10 until 20 minutes. On this slide, I show you that the recharging of vehicle is not linear. We can see on this figure that up to 80% of recharging is almost linear, but between 80 and 100% of the charging, the time cannot be controlled and depend of battery management system of the vehicle. Let's start to talk about optimization problem in smart grid related to electric vehicle. On this slide, I remind you what is the electric grid. A grid is composed of a set of production plants, such as a nuclear plant or hydraulic plant, a transportation network, a distribution network, and the final customer. As we know, electricity cannot be stored, which means that at any time the quantity produced must be the same as the quantity consumed. This is the way that the monitoring of consumption and the production is done every quarter of an hour, and the mechanism exists to balance the network if there is too much production or too much consumption. The notion of smart grid has recently emerged with the objective optimizing production, distribution, and consumption, and anticipating the balance at any moment. For this, digital ICT functions are added to the network to monitoring the network and anticipate the consumption. Now we back to the relationships between the smart grid and the electric grid. In fact, with the government prediction of massive introduction of electric vehicle in the market, this introduction may cause problem on the electric grid. For example, with the projection of 2 million vehicles in 2025, this induces an additional consumption of 4 to 5 terawatt per year. In terms of energy, this is not so much. It is equivalent to 1% of national consumption. But in terms of power, and if we assume that this vehicle charge at the same time with slow charging mode, this generates a power demand between 3,000 and 6,000 megawatts, which is equivalent to 2 till 5 additional nuclear reactors. Thus, in order to avoid the problem on the electric grid, we need to introduce a smart charging policy. In recent years, the concept of vehicle-to-grid has been introduced. It consists of a set of interactions between the power grid and the vehicle with the assistance of communication systems like sensor, smart meter, or protocol ZigBee. The objective of this interaction is that the vehicle anticipates the state of the electricity grid. Here, the vehicle can play the role of an additional energy storage system when the production is higher than the consumption, or as a system to inject the energy into the grid when the production is insufficient compared to the consumption, and also by adapting the recharging period of the vehicle during the period of low consumption. There is two types technology for vehicle-to-grid. In the first one is one-way vehicle-to-grid, in which the communication between the grid operator and the electric vehicle is used to control the charging power of each electric vehicle. And the second technology is two-way vehicle-to-grid, in which the energy is exchanged between the vehicle and the grid according to the requirement. For the one-way vehicle-to-grid, the energy flows in one direction only from the network to the vehicle. And in this case, the smart grid system can be efficient if it offers an attractive energy price policy. For example, an attractive price when charging is made in off-peak period, or penalty for charging in peak period. For the two-way vehicle-to-grid system, the energy flows in the two directions, from the grid to vehicle and from the vehicle to grid. In this case, a smart grid system can be efficient if it offers an attractive and coordinated energy exchange policy. This policy should include an attractive price either for the storage energy in vehicle when the production is more than the consumption, or for reinjecting the energy into the grid when the consumption is larger than the production. In the case of two-way vehicle-to-grid, and in order to ensure coordination between smart grid and electric vehicle, two types of architecture for coordination can exist. The first one is called centralized coordination, where the grid operator contract directly with each electric vehicle for both energy storage and energy reinjection into the grid. This architecture presents a problem of scaling up and the multiplication of several contracts. The second most suitable architecture is the hierarchical architecture, where the network operator contract directly with a recharging aggregator, which is responsible for recharging several vehicles. This architecture is the easiest to set up, since the contraction is only between the recharge aggregator and the network operator, allowing the scaling up. Slide we show the service that an aggregator can be provided and the action that can be performed in both cases of one-way vehicle to grid and two-way vehicle to grid. In the case of one-way, the aggregator can contribute to the regulation of the network frequency and valley filling. The actions that can be performed are raising and
Youssef, si Jawad, vous m'entendez?
leaving and peak shaving. The optimization problem facing an aggregator is minimizing the recharging cost of all vehicles. In this model, the aggregator collects the cost of the energy from the network operator and then submit the energy demand for recharging the vehicle. Recharge demand is calculated by solving the following linear program with the objective of minimizing the energy cost under the constraint of vehicle recharge demand, where each vehicle is charged according to its demand and departure time, and the recharge power must not exceed the available power. Other objective function can be used by the aggregator. In addition to minimizing of the cost, he can also use the maximization of revenue or the minimization of the power lost. Also, by integrating more complex constraints in the mathematical model, such as the limitation of the network power, the limitation of the power that can be supplied by the charger, and considering the demand curve, and also the capacity of vehicle, battery, and the limitation of the vehicle state of charge and the energy demand by each vehicle. In the literature, these problems are solved by optimization methods such as linear and quadratic programming solver, also by greedy heuristic and meta heuristics. An aggregator that uses a two-way vehicle to grid processes the same problem as an aggregator with one-way vehicle to grid system, but in addition, it can optimize other objective functions such as maximizing the use of renewable energy and minimizing the deviation between the consumption curve and the target curve. For constraint, in addition to the constraint of one-way vehicle to grid case, he integrates a new constraint on the bidirectional power of the charger. Again, the optimization methods such as heuristic and meta-heuristic are used to solve this optimization problem. In this slide, we consider the problem of recharging electric vehicle. This problem is a part of a collaboration project between my lab and the enterprise La Poste. Given a set of electric vehicle and a set of route, the objective here is to find an assignment of route to electric vehicle that maximize the number of kilometers done by the electric vehicle and minimize the cost of recharging of the electric vehicle. The data of the problem is as follows. For each electric vehicle, we have the following data: is capacity, the driving range, the state of charge of the vehicle, and the safety threshold of state of the charge. Each charging station is characterized by its type, even slow charging or fast charging, and the maximum power that can be delivered. Each route is characterized by starting time, ending time, and the energy demand for this route. And the grid network is characterized by physical power, subscribed power, the cost of energy, and the cost of the overtaking. Program can be modeled as the following linear integer program. The variable of the model are the following. We have three variables, xi j equal 1 if the electric vehicle j is assigned to the route I. The variable y jt equal 1 if electric vehicle j is charged at time t, and the variable p jt is the recharging power of electric vehicle j at time t. We have two lexicographical objective functions are optimized. The first is to minimize the number of to maximize the number of kilometers done by electric vehicle. Then the second objective function is minimizing the charging cost. We have here six constraints. The first constraint guarantees that each route is assigned to a vehicle. Constraint number 2 guarantee that routes performed at the same time are not assigned to the same vehicle. Constraint 3 ensure that the vehicle cannot be charged during its route. Constraint 4 limit the total power for charging the vehicle at any time t. Constraint 5 limit the power of the charger. And constraint 6 guarantee that the quantity of the energy in a vehicle is always between the minimum and the maximum state of charge. To solve the problem, we proceed in two steps. In the first one, we use the objective function of maximizing the number of kilometers done by electric vehicle. Let k star be the value of the objective function. Then in the second step, we solve again the same integer program by adding the constraint 7 there that require that the number of kilometers done by electric vehicle is at least k star kilometer, with the objective function of minimizing the total charging cost. The use of simplex solver is adapted for small instance. However, for large instance, we developed two heuristics. The first one is a sequential heuristic, and it consists in two phases. In the first phase, compatibility graph of route is constructed, where vertex represent route and two routes are connected with an edge if their time don't overlap. Then, for each electric vehicle, we extract the clique of the graph and we assign the route of the clique to vehicle. In the second phase of the sequential heuristic, and for each electric vehicle, we calculate the charging planning by solving the minimum cost flow problem. The second heuristic developed to solve our problem is the global heuristic. In this heuristic, we solve by extracting clique from the compatibility graph and assigning the clique to electric vehicle. Then, after assigning the route to electric vehicle, we construct the global charging planning of electric vehicle by solving the mean cost flow problem for all vehicles in the same time. The result of numeric experiment show that for large instance with 120 electric vehicles, the simplex can solve about 62% of instance, whereas the global heuristic solve all instances that we tested. Furthermore, the global heuristic provide the best result for all instances with an average gap of 8.8% from the optimal. To conclude this first part of the talk, as we can see, there is a lot of work developed in the literature concerning the use of electric vehicle in the context of smart grid. In fact, electric vehicles present a good opportunity for energy storage and their integration in the smart grid. However, before reaching this phase, there are still some weaknesses that need to be addressed either in literature or from technological point of view. First, there are still technological constraints for bidirectional power flow from vehicle to grid, all technology are not ready yet. Then, to develop system of vehicle to grid, where the energy flow in the two directions need a significant investment cost on the network and on the grid. In such case, development should be continued. Other critical point in the system of vehicle to grid is the degradation of the battery travel through recharge and discharge cycle of the battery, and the question of social barrier for wide participation of electric vehicle in vehicle to grid should be considered also from societal point of view. The second problem we discuss in this talk is about the deployment of the recharging infrastructure. The deployment of recharging infrastructure is a location problem to satisfy demand. This problem is known in the literature as a location and location problem. This problem is described as follows. We have a set of site candidates for installing the recharging infrastructure, a fixed or to be determined number of stations and the type of charger to be installed, a known or estimated demand for recharging electric vehicle, and have an objective function to optimize. We find in the literature three types of model: static model, dynamic models, and stochastic model. In static model, the demand of charging is known, and the problem of allocation of charging station corresponds to a set covering problem. This problem considered in the literature and known as P-center problem, and also as a P-median problem. On the left side of the slide, we can see the mathematical model of the P-center problem. It consists of assigning P-center in a network to minimize the maximum distance from each node to its center. In this mathematical problem, constraint number 1 ensures that exactly P stations are allocated. Constraint number 2 ensures that each demand is assigned to charging station. Constraint number 3 ensures that a demand cannot be assigned to a site if a charging station is not allocated in that site. And the last constraint is to limit the maximum distance from each node to its center. And on the right side of the slide, we can see also the mathematical model of P-median problem. The objective here is to minimize the weighted average distance between a node and its connecting center. We have the same constraint as in P-center problem, and the main difference is on the objective function. The mathematical problem can be improved if we add the fixed charge of installing a charging station. For instance, for the P-median problem, here the objective is to minimize the total cost. The cost consists of two parts. The first part is the cost of installing the charging station, expressed as the sum of Fj multiplied by variable xj over all j, and the second part of the cost is the cost of moving the demand to each charging station. The constraint of the model are the same as the constraint in P-median problem. When the demand is not static, the allocation of charging station can be considered in dynamic model. Here, in this model, the assignment of charging station to a site take into account on a dynamic assignment of demand of charging that change over the time. However, when the demand is not known and only statistic data are available, stochastic models are the most appropriate, and the objective here is allocating the charging station with the objective of maximizing expected covering location. To solve the location of charging station problem, several methods that are proposed in the literature. We distinguish exact method that use solver, simplex, or specific method like branch and cut or branch and price method. And we have also heuristic approach based on the classical p-median and p-center problem, and we have also several meta-heuristic proposed also in the literature. We will not give here a detail on this method. To conclude on this second term of talk about the allocation of charging station, there are several perspectives that can be tackled and interesting in the context of deployment of electric vehicle. The first perspective concerns stochastic problem. In fact, forecasting the recharge demand allows to install the necessary number of recharging stations and avoid costly investment. Another important point concerns the dimensioning the recharging station. This problem is not considered in the literature, which is important to define exactly which type of charging, like fast charging or slow charging, or how many number of charging that should be installed. And the last important point concerns the coordination between the charging operator in order to avoid a costly investment. Now we shift to another problem arising when we use an electric vehicle. It concerns the itinerary planning of electric vehicle. In the literature, the itinerary planning problem is known also as route planning. It consists of finding a path in a road network. We have a positive value on the arc of the graph road. This value corresponds either to the distance or to time. And the objective is to find the shortest path in terms of distance or the fastest path in terms of time. Finding the best path is a polynomial problem, and several algorithms exist in the literature. For example, the Dijkstra algorithm, bidirectional Dijkstra algorithm, or A-star algorithm. Also algorithm based on hierarchy contraction. However, when we use an electric vehicle, another metric is added to each arc of the graph road. Is the energy needed to cross an arc. Furthermore, the value of energy can be negative, since when electric vehicle is in deceleration phase, an energy is recovered. Then the objective is to find the energy optimal path. That means find a path that consumes a minimum energy. For such problem, Dijkstra algorithm is not valid, since we have negative value on arc of the graph. However, Bellman-Ford algorithm can be used, but its complexity is higher in n power 3. So it's needed to find efficient algorithm to find the best energy path. Before presenting the algorithm to find the energy optimal path, it's necessary to know that in the literature, the energy associated with each arc is calculated either by a ratio of consumption per kilometer, for example 154 watt per kilometer. In this case, the energy recovery in the deceleration phase of the vehicle is not considered, and therefore all the values are positive in the road graph. Or we can use a physical model of the vehicle considering all the force during the driving phase, and this model is the closest to the real consumption of the vehicle. Here we present an algorithm in n power 2 to find an optimal energy path when negative values are used in the graph route. The algorithm consists in two steps. The first step transforms the value of arc into positive value by applying Johnson algorithm. Then the second step solves the shortest path problem in the new graph using Dijkstra algorithm. Johnson algorithm works as follows. Initially, the graph, we take the initial graph, then add a node S and collect this node S to all the vertices of the graph with an arc, and the value of this arc are set to 0, then we calculate a new weight on each node of the graph. Then we transform all negative value in positive value by transformation function given in the step 4. Other algorithms for the route planning are proposed in the literature. All these algorithms are in n power 2. The first algorithm is a modified A-star algorithm without considering the battery constraint proposed by Eitmeier in 2010. The second algorithm is an extension of the first one by considering the battery constraint and a dynamic weight calculation also proposed in 2011. And the last algorithm is a modified algorithm A-star with integration of battery capacity into the cost function of the arc, and also proposed by Essner et al. In 2010. Other work on route planning problem for electric vehicle are also considered in the literature. For instance, what is the shortest path without power failure on the road? What is the energy optimal path that is x time longer than the shortest path, for instance x equal 1.05. All these problems are NP-hard since it's considered the constrained shortest path problem. As a conclusion on the route planning problem, in my opinion, several challenging problems need to be considered, and the main one, I think, is the generalization of the acceleration and the pre-processing technique used in the literature when negative value on the arc are considered. Then other interesting problems can also be considered, such as finding path with recharge. For instance, what is the shortest route with recharge? What is the shortest route with at most k recharge? Also, we can consider the cost of recharging. For instance, what is the shortest route with the lowest recharging cost? What is the shortest route with at most c as the recharging cost? All these problems are challenging problems when using electric vehicle. The last term of this talk concerns the electric vehicle routing problem. The vehicle routing problem is defined on a complete graph containing a start node, which is the depot, a set of nodes representing the customer, is to visit all the customer using a fleet of vehicles, this fleet starting and ending at the depot, while respecting a well-defined constraint and also in order to optimize one or more objective function. There are several variants of the VRP problem that are considered in the literature. This variant can be defined based on several applications, such as capacitated VRP, pickup and delivery, or split delivery. The use of electric vehicle in VRP problem add a new complexity on this problem, particularly when we use different size of vehicles battery, adding different type of recharging station. For example, how we can decide if it is possible to charge the vehicle along the route or not, or partial charging of vehicle is allowed or not, and also considering the cost of charging. In addition to the classical objective function of the VRP problem, this objective can be completed by the use of electric vehicle by minimizing the cost of routing and recharging. In this last part of talk, we will discuss some VRP problem that using electric vehicle. In this figure, we can see an example of electric vehicle route. The vehicle starts its route at the depot, visit the first customer in his time windows, then a second customer also in his time windows, Then it goes through the recharging station, where we have information about this station, such as time windows of the station opening, the power offered by the station, and the cost of charging. Finally, after charging, the vehicle returns to the depot. In the majority of studies in the literature of vehicle routing with electric vehicle, several constraints are considered. In addition to the classical constraint of the VRP, there is first of all the integration of recharge along the route. This constraint is used in the main study of the literature. Then also the integration of complex constraint. This complex constraint ranging from single type of electric vehicle and single type of recharge to several type of battery and several type of recharge. In addition, the recharge during the route can be either partial or total recharge. Finally, some studies consider the real cost of the energy charged in the vehicle, or simply a flat rate to be paid whatever the quantity of the energy charged in the vehicle. This slide will give an overview of the first work proposed in the literature concerning the routing of electric vehicle and the constraints that are considered. There are many constraints considered on these works. The first one is the composition of the vehicle fleet. That means that a fleet is composed of electric vehicle and thermal vehicle. Also, we can find the constraint on the capacity battery of the electric vehicle. We find also constraint on the time windows, constraint on vehicle capacity, and finally constraint on partial charging and different charges used to charging the vehicle. As we can see, the majority of this study use the meta-heuristic method to solve this problem. In this slide, we present an example of vehicle routing problem with electric vehicle. Here, the hypotheses considered are as follows. Each route begins and ends at the depot. Each customer is visited exactly once during the time interval 0t. At most, we have M1 electric vehicle and M2 thermal vehicle at the depot. The total duration of each route must not exceed value t. The state of charge of each vehicle must remain in the interval SOC min and SOC max. At each charging station, F charging can only take during the time windows of the opening hour of the station. And the objective function that will be minimized consists of 5 costs. Driving cost, cost of charging electric vehicle at external charging station, cost of recharging electric vehicle at the depot, fixed cost of used vehicle, and the total cost of waiting time if we arrive at the customer location in advance regarding its time window. To solve the problem, we have developed a local search meta-heuristic, and our meta-heuristic needs 3 procedures to operate. The first procedure is feasibility check procedure. For given route and given electric vehicle, the procedure return true if the route can be done by the electric vehicle K, and false otherwise. The second procedure is the recharge adjustment procedure, which calculates the quantity of energy to be injected in the electric vehicle battery on each visit to charging station, since in our model we allow a partial charging of electric vehicle. And the third procedure is charger insertion procedure, which determines the best charging station to be inserted in the route to make it feasible while generating a minimal charging cost. To initialize our meta heuristic, we developed a constructive heuristic to find an initial solution. Our constructive heuristic starts by choosing an electric vehicle according to a predefined criteria based on cost of vehicle. Then, if there is at least one customer who is not yet served, we choose a customer based on the distance. We iteratively add the customer to the active route, and also we add charging station if needed also to the active route. Then, if a customer cannot be served by an electric vehicle, we assign that customer to the thermal vehicle. In our local search meta-heuristic, we use 4 classical operators to generate a new solution. The first is the relocate operator that relocates a customer from one route to another route. We use also the swap operator that swaps 2 customers from different routes. The third operator is the to-opt operator, and the last one is the classical OR operator of the literature. In addition to the classical 4 operator, we developed 2 new operators. The first is the concatenation operator that concatenates 2 routes in one route, and the reallocation of route operator. This operator takes one route and dispatch the customer of that route on the other existing routes. Finally, all developed operators are used in a large neighborhood search method LNS that consists in iteratively alternate the destruction and the repair of the current solution until the stop criteria are reached. This method is largely used in the literature. To test our method, we use the benchmark instance of the literature. We adapted the instance used by Schneider et al. This instance consists in 3 classes of customer distribution, E, C, and RC, with 100 customers and 21 charging stations. In our problem, we considered a fleet of 50 electric vehicles and 50 thermal vehicles. Results of numerical experiment are given in the following table. We can see that operators swap, to-opt, and concate do not produce an improvement in terms of number of used vehicles, and a small improvement of the objective function regarding the initial solution. However, the local search method LNS provides the best improvement where the number of routes is divided by 2 regarding the initial solution. So, to conclude this last part of the talk, we can see that electric vehicle routing problems are widely considered in the literature, and the majority of the work concerned with the extension of the classical VRP problem by using the electric vehicle. As interesting perspective for the study of VRP problem with electric vehicle, it seems interesting for me to include first the real consumption of electric vehicle during the routing phase. In this case, the energy matrix between customers should be used and will depend on the type of electric vehicle used. Another point that can be considered is the traffic integration in the routing optimization problem. In fact, the energy consumption of the vehicle depends on the state of the traffic, and integrating the traffic in the optimization problem should be interesting to have a real traffic of vehicle. Another interesting challenge is the integration of the recharging planning of electric vehicle in the depot with the vehicle routing. And finally, the external charging should be considered with a high degree of caution, as from practical point of view, it is difficult to implement it in vehicle routing software. So I would like to thank you for your attention.
Merci. Bon, donc, I want, donc I must repeat. Donc, thank you for your interesting presentation, especially the perspective that open a large topic for research. Donc, you can ask professeur directly in English or in French. Donc, vous pouvez poser vos questions directement au professeur Ammar ou Amara en français ou en anglais. Il parle très bien les deux. C'est ça, professeur? Oui, vous m'entendez?
Yeah, there is no problem. Oui, c'est possible, ouais.
You speak English and you speak
Possible
French?
parler de... Oui, je vous entends. Est-ce que vous m'entendez là?
Oui, moi je vous entends.
Yeah, it's possible for both one.
Yes.
C'est possible pour les deux langues. Oui.
Donc voilà, vous pouvez poser vos questions en français, en anglais, directement au professeur Ammar Olamal. Avez-vous des questions? Activez vos micros pour les gens qui veulent poser des questions. OK?
OK, but I think that some question, il y a des questions sur le chat. Est-ce que c'est exactement ça?
Oui?
Ah, OK.
Le son n'est pas... On ne vous entend pas très bien, professeur.
So there is three questions. The first one, the significant rise in... Attends, je vais essayer de reprendre au moins d'enlever la vidéo. Parce que je pense que ma connexion n'est pas bonne.
Oui, professeur? Vous listen me? Non? Vous m'entendez?
Allô? Vous m'entendez?
Oui.
C'est mieux?
Je vous entends, moi. Je vous entends.
Okay. As I told you, I think that there is three questions in the chat.
Yes.
How can the first one? Will local electric grid be able to handle the significant rise in adoption of electric vehicle? How can we include this issue in the optimization model? I think this problem for the local grid, it's another problem because the first one that we discussed in the first part of the talk concerning the whole grid. When we are interested to the local grid, there is some other problem. The main problem is the balance of this local production and the connection to the grid, the global grid. Yes, I think that the local grid can handle with a large adoption of electric vehicle, but as we told it in this in the talk, there is need what do you mean that? There is the need to balancing the grid, and the electric vehicle can can play the role of storage resource. But I think that will be interesting, but from technological point of view, this is not yet available now for their deployment. So this is for the first question. The second one is a great number of researchers applied meta-heuristic to solve electric vehicle, but only a handful give solution in reasonable computational time. How about parallel heuristic for electric vehicle VRP problem? I think that in this case there is this one is another term of research about the parallel meta-heuristic or parallel model. Okay, we can use parallel model or parallel meta-heuristic for solving this problem, and we can save time to solving this problem. However, the main problem, I think, it's how we can implement this model in software for the VRP problem. I think this is the main problem, and then I think that's also okay. We can develop specific meta-heuristic for a specific problem, but when we add a new constraint, how we can adapt this this method when we integrate a new constraint of this problem. I think this is the case for all heuristic, even for parallel heuristic or for sequential heuristic.
Thank you.
Okay.
You have another question?
Other question?
Yeah,
What?
The third question.
Okay, the third question. Are data used in your research are publicly available online? Yes, it's available, but we don't have a website where this data are published. But I can give the data if someone are needed to make an experiment with this data.
Allez. Other question? Have you another
Okay,
question?
the next one.
Next. Oui. Avez-vous d'autres questions publiques? Bon, vous pouvez poser vos questions directement au professeur. It's good. Not. Bon, thank you, professeur. Donc, s'il n'y a pas d'autres questions, donc we have 15 minutes for a break, but you must prepare your coffee yourself.
Thank you very much.
Ah, d'accord. Donc, nous avons 15 minutes. Après, il y aura 2 sessions en parallèle. Bon, nous vous remercions beaucoup, professeur.
Merci
Ammar
beaucoup. C'est
Amara.
moi qui est désolé. J'ai enregistré la présentation parce que ma connexion à la maison, il n'est pas bonne.
Vous avez une question? Oui, oui.
Oui, donc la question.
Oui.
La question, quel est le coût de maintenance en fait de la batterie, sachant que vous avez dit qu'il y a une dégradation de la batterie lors du cycle de vie de la batterie, de recharge et décharge, entraîne une dégradation. Quelles seraient les maintenances et quel serait le coût de cette maintenance?
Bah, en fait, ce qui concerne les batteries, il n'y a pas vraiment de coût de maintenance. En fait, dans les batteries, qu'est-ce qu'on suppose? On suppose que la batterie, elle est utilisable tant qu'elle ne perd pas ses capacités, ce qu'on appelle la puissance c'est pas la puissance, mais la capacité nominative. C'est-à-dire si elle a une capacité de, par exemple, de 100 kWh, elle est toujours capable de stocker 100 kWh. Et généralement, tous les constructeurs, ils garantissent qu'à partir du moment que la batterie, elle perd 20% de sa capacité, c'est-à-dire si elle stocke que, par exemple, 80 kWh, Dans ce cas-là, en fait, les constructeurs, ils garantissent la batterie, en fait, ils la changent. Donc, ils l'enlèvent du véhicule, ils la remplacent par une autre. Donc, ça, c'est pour les modèles avec, que ce soit par la location de batterie, par exemple, Renault, elle fait ça. Il y en a aussi des constructeurs, même s'ils vendent la voiture avec la batterie, il y en a des garanties sur le véhicule. Tesla, elle garantit ça aussi. Donc, dès qu'il y en a la batterie qui elle se dégrade, c'est-à-dire elle perd de sa capacité nominative, les constructeurs la remplacent. Donc, les batteries, en fait, les batteries qui sont remplacées, elles ne sont pas jetées parce elles ont déjà 80% de leur capacité de stockage. Et ces batteries-là, souvent, elles sont recyclées dans un deuxième marché, ce qu'on appelle le marché de stockage d'énergie. Donc, ces batteries, elles sont toujours valides. On peut stocker de l'énergie. Donc, c'est le deuxième marché pour ces batteries-là. C'est le stockage stationnaire, c'est-à-dire elles sont connectées entre elles, sont mises dans un dépôt et elles sont spécifiquement utilisées pour le stockage et le déstockage de l'énergie.
Ok, merci, professeur.
Merci, monsieur le professeur.
Autre question?
Une dernière question.
Oui?
Oui, quel serait l'impact en fait de recyclage des batteries sur l'environnement?
Il y en a beaucoup d'études qui ont été faites là-dessus sur le cycle de vie du véhicule électrique et le cycle de vie des batteries. Après, on n'en a pas encore un recul suffisant. On peut dire que le recyclage des batteries, il coûte cher, ça pollue l'environnement, mais tant qu'on n'a pas utilisé dans un deuxième marché qui est de stockage de l'énergie, elles ne sont pas utilisées massivement. Donc, on ne sait pas trop. C'est vrai que les études disent que le recyclage des batteries, c'est un autre manche du problème. Mais on sait bien que les choses évoluent très vite. Un exemple très simple, c'est que les batteries, il y a 5 ans de ça, c'était pratiquement $1000 le kilowattheure d'une batterie. C'est-à-dire pour fabriquer une batterie, il faut à peu près $1000 ou 1000 € pour fabriquer un kilowattheure de stockage d'une batterie. Ça, il y a 5 ans de ça. Et ça en 2015. Et aujourd'hui, en 2020, on est descendu à 150 € le kilowattheure de stockage. Donc, on voit bien que le coût de fabrication des batteries, il a descendu énormément. Donc, on peut imaginer que aussi, dès que le besoin va se sentir à un certain moment, même si le recyclage des batteries, peut-être il est un peu cher, il est polluant en ce moment, mais tellement les technologies ils avancent vite qu'on peut espérer que d'ici 4 ans, 5 ans, le recyclage des batteries, ça ne pose plus ce problème-là environnemental qu'on a actuellement.
Merci pour votre présentation.
Merci, professeur. Donc, autre question? Est-ce que vous avez d'autres questions? Non? Pas d'autres questions? Bien, donc, sinon, nous vous remercions une autre fois, professeur Ammar Oulamara.
Merci beaucoup.
Et donc, vous avez jusqu'à 10h30. Donc, tout le monde a jusqu'à 10h30 pour avoir une pause. On dit une pause café.
Est-ce
Mais
que, juste une question,
oui,
Est-ce que cette session, elle va être tout de suite fermée ou vous laissez ouvert? Peut-être éventuellement, il y en a certains qui veulent poser une question en privé ou quoi que ce soit après les discussions là. Je reste de toute façon connecté si éventuellement, s'il y en a certains qui veulent continuer la discussion.
d'accord. Donc, merci de votre patience. Et donc, on a jusqu'à 10h30, il peut être rester ouvert jusqu'à 10h30, puis on aura deux sessions en parallèle. À 10h30, on va fermer cette session pour ouvrir deux autres en parallèle, puisqu'on a deux sessions en parallèle. Ça va? Donc, s'il y a des gens qui veulent poser des questions, ils peuvent les poser, mais jusqu'à 10h30. OK? Ça va? Vous m'entendez, professeur? Non? C'est déjà coupé? Si Youssef? Si Youssef? لا تقطع عليه قال لك bon voilà bon ok donc monsieur Ammar vous m'entendez monsieur Ammar vous m'entendez bon je pose la question monsieur Jawad tu m'entends Hassan tu m'entends Bez
Oui, 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 monsieur, oui, oui.
tu m'entends donc je ne
Oui,
sais
là.
pas pourquoi les autres non j'entends pas les autres donc professeur Ammar tu m'entends vous m'entendez Je crois qu'il y a un problème de connexion. Vous m'entendez, monsieur Ammar?
Il n'est plus connecté. Il a quitté la réunion.
Quoi?
Monsieur Ammar a quitté la réunion.
Bon, mais il a quitté la
Il y a un
réunion.
problème de connexion.
Bon, d'accord. Donc, de toute façon, la session est ouverte jusqu'à 10h30. Si par hasard le professeur Ammar ou l'Amara donc, rejoint la réunion, donc s'il y a des gens qui ont des questions pour lui, ils peuvent les poser jusqu'à 10h30. Et à 10h30, on a deux sessions en parallèle. Bien sûr, nous devrons quitter cette session pour rejoindre une des deux sessions. Bien sûr, on ne peut pas rejoindre les deux en même temps pour ne pas avoir de problème de son. D'accord? Donc voilà, à tout de suite. Donc à 10h30.